Well, good morning, everybody. We are so excited that you are joining us today. Today, we're going to be looking at differentiation and integration as we continue this week's theme of connecting AB to BC, where each day we look at an AB topic from the curriculum and then do a quick review of that and then make some connections with that topic to other topics in AB, as well as connecting that to topics on the BC exam to help you get prepared for the 2020 AP exams. As always, our materials should be in the little link underneath our videos. If you click on the link, you'll be able to find the handouts from today with a whole bunch of problems that we'll be doing today, as well as many problems that we won't even get to. And then the solutions are posted each evening around 9 p.m. Eastern time. So I am, as always, joined with my co-host, Tony Record. Tony is a teacher at Avon High School, and I'm a teacher at Speedway High School. Both of us are from Indiana. And Tony and I have been doing these sessions now for about 3 weeks, and we're excited that during these review times, we're working together. And it looks like, well, Tony might be having some technical. Tony, hey, I don't think your camera's on. Tony,
what does this button do? What start video? Start video.
Grover, is
this on?
Yeah, Grover, Grover, you're way too close, man. You got to scoot back a little bit. Scoot back. There you go. There you go. Grover.
Hello, Bryan.
Hello, Grover. I was expecting Tony this morning. What are you doing here?
Well, I'm traveling to talk about my book, The Monster at the End of the Book. Have you read it?
Yes, I have actually. And Grover, it's really odd that you're here, really unexpected, right? And I know a lot of calculus teachers who are watching, and probably a lot of calculus students have actually read your book. And so I'm sure they're really excited that you'd be doing a book tour and walking around and meeting with them. But is that even okay? Aren't we on like a social distancing? Is that safe to be going on a book tour right now?
Oh, Grover have secret. I'm a Muppet.
Oh,
good antibodies.
Yeah, I gotcha. Okay, that makes a little bit of sense, I guess, right? Well, Grover, I'm surprised. I'm a little bit shocked that you're here. I'm not sure what to do with that, but Tony and I were going to be doing a calculus lesson today. Do you think maybe you want to stick around and try your hand at that and maybe teach some calculus today?
Grover, try. Yes.
You're good at calculus?
Baby, I think so.
Well, here's the beginning of it. Tell me if you can handle this, and if you can, then maybe we'll get a nice lesson from Grover this morning.
Let me see. Grover doesn't know how to do this. Grover doesn't know calculus.
Oh, Grover, don't be sad. I'll tell you what. Do you have a little bit of time before your next book signing? Can you stick around maybe and then let Tony teach you and let us, maybe Tony and I together can teach you, and maybe you could actually learn some calculus today.
Oh, yes, Grover, like that very much.
Well, that's awesome. That's perfect. You think maybe you can, is Tony around there? Have you seen him anywhere?
Yes, I go get Tony. Tony!
Oh, we lost Grover, I think. Hopefully he can find Tony. I don't know.
Here I am. Hey, thanks, Grover. Hey, no problem. Just don't touch that. I tell you what, sit right there, and Bryan and I will teach you some calculus just like the rest of the folks. How's that? Oh, gosh, sorry about that. I let him near the control station when I was going to fill up my cup, and who knows what would have happened. So, all right, so where are we? Derivative rules, is that where we're at, Bryan?
Yeah, I think that's where we're going to start off. I thought maybe we were going to get a special lesson from Grover today, but I'm glad that you're here. I was getting a little bit nervous.
Well, he's got his pencil, he's got his handout, so he's ready to go. So what do you say we take a look at these derivative rules? And we've got these classified into tier 1, tier 2, tier 3. And the tier 1s are the must know, right? Those are the ones that we definitely want to go into the AP exam having quite a bit of confidence on. And the tier 2, helpful to know. I'd say any good calculus student, it would be a great idea to have these under your belt. But any given year, you might see maybe a couple of these show up every now and then on the AP exam. This year, could be an exception, could not be an exception. You know, we just have to wait and see. And then the tier 3, the honorable mention, those are the guys that, hey, as any calc student, you know, it's great to know those, but they're very, 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 very unlikely to appear on any year's AP exam. This year's included. So let's go ahead and start off with some quick check. How about that? We've got quick check 1 here, and let's take a look at part B to begin with. So we have some values in a table, and the question reads, the functions f and g are twice differentiable for all values of x. Selected values for f, g, and their derivatives f prime and g prime are shown in the table. So if we take a look at part C, the thing that we want to kind of capture here is the strategy by which we're going to take this derivative. And we have c of x defined to be f of g of 2 of x. So a lot of stuff going on there. And this is just a tailor-made chain rule problem, but it's got even a little bit more of a twist to it because of the layers of the function that we have. So if we take this derivative, c prime of x, what we have going on is that we first of all have to take the derivative of the outer function. There's so many analogies to these, like peeling an onion and using Charms Blow Pops or M&M, peanut M&Ms. Maybe I'll use that analogy when we're finished here. But if we take that derivative of that outer function, f, and we have f prime, all of the inner function stays the same. You can almost think of that outer function as like being the candy shell of the peanut M&M. That's the first thing that you're going to taste. That's the first thing that's going to make contact with your mouth. All of the stuff that's inside that M&M is not going to change, right? The g of 2x is going to be the same. And then we would multiply that by, now we're into that chocolate around that peanut, right? The middle part of that. So we would take that derivative of g in this case, whereas the peanut, the 2x, is going to stay the same, right? He's still in there. And then finally, we get to the end and we can take the derivative of that inner part, that 2x, which in this case is going to give us 2. And now we have completed this, what sometimes we refer to as maybe a double chain rule type of derivative. So next we can go ahead and plug in our 2 for x. And upon doing that, we would get f prime of g of 4 times g prime of 4 times our 2. Now we wouldn't be finished yet. We wouldn't be able to get full credit for this problem until we evaluate those particular functions. So g of 4, we go to the table, we end up getting a 1. I'm sorry, g of 4 is a 0 rather. So f prime of 0. And g prime of 4 is going to take us to the bottom row of the table, and that gives us a negative 2. Make sure we drop down that other 2. And then for our f prime of 0, we're going to slide across this row. We see that f prime of 0 is 3. So it looks like when all is said and done, we would have 3 times negative 2 times positive 2 in this case, I believe, and that would give us a negative 12, unless I've made a terrible mistake. I think that's right. Grover agrees. Okay, so Grover, you're learning. Good. All right, let's go ahead and take a look. Why don't we move down to D? I think Bryan and I talked about this would be a pretty good one to take a look at because it's going to utilize a very popular derivative formula, right? The derivative of the natural log of u. And if you want to flip back to your tier 1, tier 2 honorable mention chart, you'll see that this is definitely in that first column, and that the derivative of the natural log of u, sometimes we think of it as u prime divided by u. So if we go about our business and take the derivative of n of x, so I get n prime, the u in this problem is going to be this f of x. So by virtue of that formula, we can call this derivative u prime or f prime of x over f of x. Now all that's needed to be done is we insert 4 for our x, and we have something like this. And then at this point, we just can go to our chart and see what we've got. F prime of 4, looks like that's going to be a 15 from the chart. And then for the f of 4, you always have to make sure that you're going to the correct row. And 15/5 would be an unsimplified correct answer, but if we simplify it, we would get this nice value of 3. All right, we encourage you to take a look at the other two problems in Quick Check 1 that we didn't check out today. Let's take a look at Quick Check 2 and maybe look at just a couple of more here. A couple of different things going on with Quick Check 2. First of all, we are given a pair of graphs. So it reads, the functions f and g are continuous on the closed interval -3 to 6, and the graphs of f and g are shown in the figure above, and each consists of 3 line segments. So looking at h of x, defined as f of x squared, and we're asked to find h prime of -2, we go about our derivative and we develop our strategy again. And our strategy is going to be that of a chain rule, because we definitely have a composite function here. Outer function, this function called f, the inner function is this value, or this expression x squared. So if we take that outer derivative, f prime, keeping the inner part the same, right? We'd have f prime of x squared, and then we take the derivative of the inner part to get 2 times x, and then we can finish it up by replacing the x with -2. And -2, of course, squared would be a +4. 2 times -2 is -4. And then we would go down to our graph. Now the graph is set up so that we're looking at a graph of f of x and g of x, right? So if we want to find f prime of 4, so we have to follow along this particular path of the f graph, and right here is where 4 is, but you want to resist the temptation to call that 1, right? Because that would be f of 4. We instead have to look at what the slope of this piece of this graph is going to be, which at this point is down 1, right 1, so that would be a -1 slope. And of course, when that's multiplied by -4, we get a result of +4. Okay. Let's do one more here before we turn it back over to Bryan. Let's take a look at part C, because part C for the first time here today is going to have us exercise the usage of the product rule. And we have our p of x function now defined to be f of x times g of x. And we're going to evaluate this for p prime of 4. So if we take the derivative in general of p prime of x would equal, you could set up your product rule a couple of different ways. I'm going to choose to take the derivative of the first function times the second function. And then we add to that the first function multiplied by the derivative of the second function. And of course, a lot of textbooks might switch the order. The commutative property is alive and well in this particular problem with the product rule, not so much in the quotient rule, so you have to be careful about that. And we insert 4, and we have f prime of 4 times g of 4 plus f of 4 g prime of 4. And we again read right from the chart. I think f prime of 4, we've been there just a moment ago. We have that -1 slope. And for g of 4, boy, talk about switching gears here. Not only do you have to switch to the other graph, but you also have to realize you're looking straight at the y value now, so -2. And then for the f of 4, we're back up here, looking at the value on the graph, +1. And then for g of 4, well, we get down here and we realize, oh, the slope to this piece of the graph is just going to be a 0. So when we simplify that expression, we get +2. And it's very possible that throughout the year, you've seen instances of product rule, quotient rule used in this fashion with charts, maybe with graphs. Teachers out there, it seems like we can never have too many of these. So you've got an excellent collection of problems that you can still inject into your curriculum in the future. But it's a really wonderful way to test these concepts, again, without giving the students that analytic approach, that algebraic piece that they could manipulate so easily with a calculator, which we know is something that's just not going to happen on this year's AP exam. So, and I think Bryan's now going to take it away and do a few other quick checks beyond, I think, quick check 4, if I'm not mistaken. Is that right?
Absolutely, Tony. And so we're going to make a quick transition now to integration. So Tony did a great job doing a nice refresher on some of our derivative rules, the main ones. And then especially, I hope, and Tony mentioned this, but I want to make sure that you heard what he said, because it was so apropos for how this exam is going to be this year, that we're going to see a lot of graphical and tabular questions like Tony just looked at, because that's how we can really check for your understanding during one of these take-home style tests, when we know that you have access to Google or calculators or even those apps on the phones now that will solve problems for you. These are the kind of problems that are going to be not able to get around the math. You're going to have to show that you can do these problems, and those other resources aren't going to get you to the answers like your own understanding will. So as we do that, we're going to keep that same mindset, and we're going to look at some integration rules, and then we're going to take a look at a couple examples here where we're going to see how this integration might appear in a lot of different ways. I always love integration because I always feel like it's like a detective story to me. We're trying to figure out the best approach. Derivative rules are a little bit more straightforward because you recognize the rule and you apply it. Whereas integration, since we're doing anti-differentiation, it's a little bit more problem solving in the beginning, but the calculations are a lot easier once you identify what type of problem it is. And so just like before with integration, I like to break up my problems into 3 tiers. And I call it the big 5 is tier 1, because if you look at past exams, the actual integration formulas that you have to know, about 90% of them, of the problems on AP exams, come from these 5. And if you know these 5 integration rules, you can get through the vast majority of actual AP questions that involve integration. And the nice thing is they're just the same exact formulas as our derivative rules. And I even put them in the same order. So if you know your derivative rules, the antiderivatives are just going in reverse. And so these are going to be the big ones, recognizing those. And then tier 2s are what I call helpful to know, kind of like we mentioned before. You might see a question on there. They're not as common. And then tier 3, you're probably not going to see a problem like this on an AP exam, but certainly in college, a Calc 1 or a Calc 2 or a Calc 3 course might expect that you have these known for future coursework. So the big idea with integration rules is going to be this U substitution, right? Notice I didn't use any X's in any of these problems. They're always U, because the questions never look this simple, do they? That's the problem with integration. And it truly is anti-differentiation. Derivative problems always start out kind of simple and clean and nice, a very kind of small problem. And then when you apply the derivative rules, they expand and sort of get uglier, right? Whereas integration is the opposite. The problems look expanded, they look kind of ugly and complicated in the beginning. And our job is, before we even start the calculus, simplify, reduce, and clean up the problem so that we can apply one of our basic integration rules. So when you're doing integration, don't be so quick to start the calculus part of it. Start thinking about the structure of the problem. What do I recognize? Can I do U substitution? How can I clean this problem up so it becomes a little bit easier to handle? So we're going to look at several different examples. And just like with the ones that Tony was doing with us, you're going to see 2 problems per page, and we're going to just do 1 of each page. So you can go back later and try the other problems as some additional practice as you're reviewing these ideas. So quick check number 4 is a table problem, and it says we're integrating here on the left-hand side the integral from -1 to 2 of this f prime of 2x e to the f of 2x. And my first instinct was, oh man, if I flip back to that previous slide, that wasn't my big 5. You know, Brian, you told me these big 5 are going to be the main 5 problems that we should know. This doesn't look like one of those. It wasn't in tier 2 or tier 3. This is what I mean by cleaning the problems up first. On the surface, they look ugly, they look complicated. But if you step back and think, okay, what type of those big 5 problems do I notice? And I notice this e in the problem, which makes me think this is going to be of that form, the integral of e to the u du, right? That's the one of the big 5 that it is. And so we're going to do some u substitution. So whenever I see like an integral involving e, typically the exponent of e becomes my u substitution. So here, I'm gonna do a little bit of side work, and I'm gonna say, well, then I'm just gonna trust the process, right? I don't quite know how it's gonna turn out, but what if I set the exponent of e equal to u? And then when I do u substitution, I immediately have my students find du or u prime. You might call it different things, but we're going to call it du. I was doing derivatives earlier, so that's why I was calling things u prime. And then the derivative of f of 2x is going to be 2 times f prime of 2x dx. And every teacher, I feel like, teaches integration a little bit differently. So if this looks different than how you learned it, I think Tony hit the nail on the head yesterday when he said, if what you're doing is working for you and you're good at something, certainly don't change what you're doing. There's different approaches. This is how I teach it. So don't worry if it looks a little bit different. I make my students, once we have our du, we don't go on until we make sure in the integrand we have exactly what du equals. I have to have this 2f prime of 2x dx. I've got everything I need. I've got my dx here, my f prime of 2x. I'm just missing the 2. I wish there was a 2 in this problem. And so I like to just say we're kind of the god of numbers in math, right? In calculus, we're kind of the god of numbers, meaning if we wish there was a number there, we can create one into existence, as long as we balance out our universe, our math universe, by canceling it out in front. So if I wish there was a 2 there, poof, we can create the 2 that we need as long as we keep balance by putting a 1/2 in front. And I always say we're the god of numbers. We're not the god of variables, meaning if we are missing an x for our u substitution, we don't get to create an x and then divide by an x out in front. This only works with constants, right? Using our properties of integration. And so by doing this, I've now got this in the proper form. And so we're going to rewrite this in terms of u. So if I rewrite this in terms of u, I have e to the u. And then remember all that other stuff I underlined in blue, that was just du. So all of this ugliness became something very simple like this one right here. And so now all we have to do is make sure that we change our limits as well. You'll notice I didn't write those limits on there because the -1 and the 2, those correspond to x's, right? Every integration problem has 3 pieces, right? Every integral has a differential at the end that tells you what variable you're integrating with respect to. It has an integrand, which is the expression that you're integrating, which has a variable, and then it has limits, right? And all 3 of those things have to match up, meaning in this case, all 3 of those are in terms of x. So if I'm going to rewrite my problem in terms of u, we've got to make sure we remember to change those limits. And on an AP problem, a lot of times what my students will do is they'll keep those -1 and the 2 on there, and then they'll just convert things back to x when they're done. And that's a fine idea. The problem is if you write -1 and 2 on there, you've now told us that your limits for u are -1 and 2. That's a false statement. And there's going to be a penalty on the scoring of the exam because you've written something that's not true, even if you convert back to x later on. And so what I like to do is just go ahead and change those limits to be in terms of u. And then we can change those limits by using our formula here. U is equal to f of 2x. And so when the lower limit was -1, that means that u is going to be f of -2 if I plug -1 in there. And then going to our table, we can see f of -2 is just 1. And the upper limit, when x is 2, we get u is f of 4. And at my table, f of 4 is just going to be 0. And so my limits here, my lower limit becomes 1, and my upper limit becomes 0. And notice how I put the lower limit as 1 because that's what the lower limit became, right? Even though these are sort of what we would call flipped from how we normally like to have them, we like to have the lower limit on the bottom typically, we have to put them in the corresponding place. If you want to flip these around, we can do that using another property by making the integral negative in front. But if we're going to be applying the fundamental theorem of calculus, guess what? We don't have to flip those limits, right? The fundamental theorem of calculus works no matter how the limits go. So I'm going to leave my limits like that for now, and then we're going to integrate this using one of our 5 rules. Well, the integral of e to the u, now that we have it in proper form, I love e to the u because the integral of e to the u is just e to the u. And then my limits are going to be from 1 to 0. And as always, we plug in the top limit first. So we're going to get 1/2 e to the 0 minus 1/2 e to the first power. And on an AP test, this is numeric, meaning you could type that into a calculator, right? There's no variables there. I know a lot of times students think e is a variable, but it's just a number. So you could leave your answer like that. If you wanted to simplify it, you could. It would just be 1/2 minus 1/2 e would be another acceptable answer. So that would be a good example of u substitution. If we jump to another problem here on same quick check, but we're going to go to part C, so same exact table. It's a different approach, right? Because we don't have one of our 5 forms. We don't have any e's, cosines. We have this function f double prime of x in the problem. And My first instinct with any integration problem, whether you're in Calc AB or in Calc BC, is look for those parentheses, right? When you see things in parentheses, that's usually a sign that you might be able to use U substitution. And I always check that method first. I think sometimes in Calc BC, we get so focused on these BC ideas like integration by parts, right? That we always want to make everything integration by parts or something like that. And so every time we see a product, we try to take that approach when the U substitution is still going to be a very, very common technique. It should probably be our first thought no matter what. And so if I look in parentheses, the things inside the parentheses are usually going to be what we set equal to U. And I always do a quick check to say, well, if the inside is U, is the derivative of that floating around on the outside anywhere, right? So if U is x squared plus 1, U prime or du would be 2x. Well, there's my x right there, right? So as long as you have the variable, we can fix the number, right? We don't always have the right number, but remember, we are the God of numbers, so we can create the numbers we need to make the problem work. And so I'm going to go ahead and try U substitution again on this one. So we have U equals x squared plus 1. And that means that du is going to be 2x dx. And just like before, I need to make sure I have my du in the problem before I go any further. There's the dx that I need. There's the x that I needed. And then I'm just missing the 2 in front. So if I put the 2 there, right, I kind of squeeze it in there, multiply by 2, then I can multiply in front by a 1/2, because if we try to create a number that we need, we're going to have to offset that product, right? We're always allowed to multiply and divide an integration problem using our properties of integration. And so now that we have this, we can go ahead and rewrite this problem. So this is going to be a 1/2 in front, and we're going to write it in terms of U. So we have f double prime of U, and then notice everything on the outside, just like before, just turns into du. And then we still have to change our limits to be in terms of U. I always think it's helpful to make everything in terms of U. If you're doing definite integration like this with U substitution, change those limits. And I'm going to encourage you not to go back to the X versions of those, right? A lot of students will convert things to U, they'll integrate it, and they'll convert it back to X to plug numbers in. Remember, U is the simpler form. So keep it in terms of U. It makes your math a lot easier on the back end. And so if I go ahead and rewrite this, the lower limit was -1. So if I plug that in for my X value, my lower limit is going to become 2. And if my upper limit was 0, that's going to become just 1. And so my lower limit is 2, my upper limit is 1. And now we're able to go ahead and integrate this using the fundamental theorem. So the integral of f double prime, notice in the table, we have a row of f prime. Sometimes students, this is always like a big trap, right? We do all of this front work using U substitution that when we finally convert things to U, we feel like we've done so much work that we try to just plug those numbers in. We want to just plug the limits in thinking, oh, I've done a lot of work, I should be plugging things in about now. But remember, we haven't actually done any calculus yet, right? We have to integrate this function first. And so don't try to plug numbers into there before you integrate. And so the integral of f double prime, well, this is a nice conceptual example because it's not one of those tier 1, tier 2, or tier 3s. It's just understanding how our charts work, right? What's the antiderivative of f double prime? Well, that's just going to be f prime, right? And then we're going again from 2 to 1. So we're going to have 1/2 f prime of 1 minus 1/2 f prime of 2. And notice, again, I didn't have to flip those limits, right? Because the fundamental theorem takes all of that into account. Now, you certainly can flip them. If you want to flip them and put a negative and 1/2 in front of your answer, you're going to get an equivalent answer as doing it this way. And now going to our table, we have to have some numerical values before we're done. And so 1/2 f prime of 1 is going to be 1/2, and let's look the table carefully. F prime of 1 is right there. So that's going to be -4. And then minus 1/2 times f prime of 2, and f prime of 2 is 1. As soon as I'm at this step right here, we could leave it because this is a numerical answer. There's no need to simplify. But Tony and I are math teachers, and it's really hard for us to not simplify things. In my class, and I've heard Tony say this too on the air, as well as some workshops we've done together, we catch ourselves saying things like, we don't have to simplify this on the exam, so we can leave it just like that. And you kind of like will notice a brief pause, and then we can't control ourselves. We have to go back and actually simplify, like, okay, but I'm going to do it anyway. But you don't have to simplify it. And on a time test, a 45-minute test, we know this year's test is 45 minutes, and we also know it's going to be a full 45 minutes, meaning they want to give you a test where you have a chance to work the entire time. So anytime we don't have to simplify, it might save you a few more seconds to think about some of the more challenging problems that come up. So moving on to quick check number 5, these are going to be some graphical examples here. And what I would like to do is skip we were going to do part A, but I want to skip this and move on to part D, only because Tony has a really good FRQ problem that's going to tie a lot of this together. So I want to make sure we get to that and possibly even a part of the one that I was going to do at the end. And so, but I want to show you one graphical example. And I'm going to go through a little bit more quickly now because we've done U substitution several times. I see my parentheses, and so my natural instinct, hopefully you see it too, is that the U is going to be whatever was inside the parentheses. And then immediately once you find U, I just figure out what the derivative is of that expression or that equation, and I get 2x dx. I look at my problem and I say, hey, do I have a 2x dx there? I've got everything I need but the 2. So I'm going to put the 2 there, and I'm going to put the 1/2 in front. As I'm looking back and doing these problems, I'm realizing I must like that 2 and 1/2 combo because all the problems we've done have had that same fix, right? That's not a general rule for AP exams. And then now that I have this, I'm going to rewrite this in terms of U, and it just becomes f of u du. And then my limits, again, if I replace my limits, the lower limit 3 is going to become 6 because 3 squared minus 3 is 6. And my upper limit of -1 is going to become -2. -1 squared minus 3 is -2. And we get -2 up here and then 6 down here. And then this is the one case where I encourage my students, you don't have to do this, but I see a lot of mistakes on exams and with students if they don't flip the limits in this case. And so why was it on the first 2 examples we did, I didn't flip those limits when the lower bound was bigger, right? We like to have that lower bound smaller normally than the upper bound. But when you're applying the fundamental theorem, where you integrate and plug those numbers in, it doesn't matter what order they're in. As long as you do the math correctly, you'll get the right answer. In this case, we're not going to apply the fundamental theorem. We can't actually integrate f. We're not going to integrate f because the integral of f would be like capital F. Well, I don't know what capital F is. What we're given up here is a graph of regular f, right? And so if I integrate this, it becomes capital F, and I'm not sure how to find that. However, the integral of f, if you're given a graph of f, remember the integral of a function is just going to be the signed area between the function and the x-axis. And so the integral of f is just kind of the area model of the graph of f. So whenever I'm doing the area model, not the actual fundamental theorem, that's when I like to make sure my limits are in the proper form, because then I like to always go from left to right. And I know that a lot of teachers will teach that you can go from right, you can go backwards, is fine as long as you make your answer negative. All that's fine. But what I found is when you start going backwards, you don't flip those limits, you have to make your whole answer negative. Plus you have some parts of the area that are negative. You have all these negatives and negatives, and it gets a little bit confusing and a lot of mistakes happen. So I like to make these examples the lower limit on the bottom smaller. So I'm finding the area starting at -2, and I'm going to 6. The integral of f from -2 to 6 is just that signed area. So we're going to have a -1/2 in front. And then if I go ahead and do this, remember this part right here is below the x-axis, right? It's a part of the graph below. That's why I mentioned the signed area. So I know the area is positive, but the integral is the signed area, meaning if the part of the area is below, it's going to give me a negative integral. And then the second part of the area is above the x-axis, and we get a positive 12. So in this case, I am going to leave my answer like this, so I don't have to deal with simplifying it on live YouTube and making a mistake. So Tony, I think you're going to walk us through a couple of practice problems on one of the FRQs. Is that correct? That's going to tie some of these ideas together?
That is correct. On our BC1 and BC2 questions that you have access to, it looks like 4 of the parts are going to tie into AB topics specifically, and then 2 of the parts will tie into a BC topic. And I think I'd like to jump ahead here to part C, if that's okay, and read the stem here very quickly for BC1. It says the function f is twice differentiable in the closed interval -5 to 10. The graph of f is given. We also know that we have horizontal tangents at -5, -1, 2, 6, and 9. And the areas bounded by the graph of f of x and the x-axis are provided in the figure. The twice differentiable function h is defined as follows, and it is known that f prime is 0 is 4. So a lot of stuff going on there. We just have to use that information as it occurs in our problem. So for part C, we're going to define k of x to be h of x over 2x. And we know that the integration from 0 to 2 of f of x is 5. And from that, we want to find k prime of 4. So finding k prime of 4 pretty much takes us back to this beginning function, and that we want to take its derivative. So we develop the strategy by which we're going to do that, and we can see that this is certainly a quotient. So we'll use that idea of the quotient rule, and I will start it off by taking, say, the derivative of the top multiplied by the bottom. Those can be reversed if you like to do the high d low minus low d high. And then make sure you put a subtraction in. And then we have the numerator multiplied by the derivative of the denominator. And of course, all of this would be put over the denominator, which in this case is 2x quantity squared. So it seems like a very easy start to the problem. Just know the quotient rule and move on from there. And then let's go ahead and plug in 4 for x. And so all of these x's are going to be changed to 4s. And I think I might go ahead and do any kind of arithmetic that I see. And let's see, in the denominator, we could probably go ahead and take care of this. 2 times the 4 would be 8. And once we squared, that of course is 64. So now really the only thing that's holding us back is finding h prime of 4 and finding h of 4. So let's look at h prime of 4 first. So we go back to this function defined by this integral h of x, and we see that, oh, well, if we want to find h prime of 4, we first of all have to consider what is h prime of x. And we've been here before. We've had a couple of problems like this in some previous videos, but we're going to use one of our fundamental theorem of calculus ideas, and that would allow us to take this upper boundary and then replace our independent dummy variable t with that. And that would give us f of x over 2 in this case. But because that upper boundary is something a little bit more significant than just an x, we are forced to take his derivative and multiply by him using that chain rule. And that works every time as long as your lower boundary is some kind of constant. All right, now we're supposed to figure out what h prime of 4 is from this. So let's say if we enter a 4 for this x over here, we'd have 1/2 times f of 2. And f of 2 can be read from the table, or I'm sorry, from the graph. If I just scroll up a little bit, here's 2, here's our function f, and it looks like we have a y value of 4. So 1/2 times that 4 would be a 2. So we can certainly replace this h prime of 4 with a 2, and of course there we get 16. So this is kind of what I have so far here. I'm now waiting on figuring out, well, what's this 2 times the h of 4 going to be? And that brings up another very interesting situation. So we figure out, all right, well, what is our h of 4? I'll kind of work this off to the side. And we see that, well, here's our function h of x defined by this integral. All that we're needing to do is replace the x's with 4. Seems easy enough. So we do that, and we now integrate from -2 to +2 of this function f of t. And as Bryan indicated earlier, we just can't integrate f of t. We don't know what his antiderivative is, but we do have this wonderful graph of f, and we have some very powerful information about the areas, but there's a little bit of a problem here. If we try to integrate from -2 to +2, well, finding that definite integral, that signed area from -2 to 0 is pretty easy, but boy, do we have a hard time figuring out what this area is going to be without knowing the equation of that curve. Now you want to use the idea that you have this information, the integral from -2 to 0 at your disposal. And well, you would think that this piece of information would get used for something if it was mentioned in the problem. And that's where we're going to be able to tackle this problem. We're essentially going to use an additive integral property that just says, all right, if you want to integrate from -2 to 2, go for it. Just start from integrating from -2 to 0, and then add to that the integration from 0 to 2. Just pick up where you left off and finish up your interval there at an upper bound of 2. And so we can see that the first definite integral gives us a signed area 2.5, but below the x-axis, so that's -2.5. And then we use the idea that the integral from 0 to 2 is +5. And of course, that's going to be +2.5. Now, if that is our h of 4, once we multiply him by a 2, that of course gives us 5. If you don't want to simplify, that's fine, but it's not very difficult to get that 11 in the numerator. So I really like that problem. It does throw in a lot of different obstacles for the student to overcome to piece this solution together. And let's go ahead and look at one very, very, very quick BC question. I'm going to look at BC 1 problem. How about problem F? A few days ago, we had a little conversation about arc length. So we're kind of doing the same thing here with a slightly different environment. Set up, but do not evaluate an integral expression in terms of f that would give the arc length of the function h from 0 to 12. So if you remember our arc length formula, we could say L or S or whatever you want to call it, and it sets up as a definite integral over some boundaries that not all the time are given, but many, many cases they are. So there's nothing that we really have to do about that. We just know we're going to integrate from the 0 to the 12. And we know that the formula is the square root of 1 plus the function's derivative squared. All right, and that function's derivative here is going to be h, right, or h prime. So we have to concern ourselves with what is h prime of x? Well, if you recall, we just did that a moment ago, right, in our part C. So you can just borrow that result, which if you remember was f of x over 2, and then we multiply by the derivative of x over 2, which is 1/2. So if you can just place that inside that integral and square it, you've got the result that you want. You can write it a variety of ways, just want to be very careful. Let's say if we square just that part, and then for the denominator of 2, we can actually do the simplification for that square. That might be probably the most concise way to write this final answer for just the integral setup. All right, and I think at this point, Brian, you're going to take some parts of BC2 and discuss them, huh?
Yeah, we're going to go through just a couple of quick parts on BC2. And Tony, this is a miracle because we're actually pretty close to being on time. And so I'm not going to talk for 5 minutes now just to waste that time to make sure we kind of push past the boundaries. But we're doing well on time. And so as a reward to all the students and teachers, at the end of our lesson, I've got a special surprise for everyone, introducing a new twist to our segments possibly. So stay tuned to the end and we'll get that to you. So since we're on time, we can do this. So this is BC2, another FRQ. And just like Tony mentioned, it's got several different connections between A, B, and BC. Really good practice problems to get you ready for the exam. So we say this every single day, but we cannot stress enough how valuable we think doing these FRQs that we're sharing with you will help you on this year's test. Any exam really, but this year's test in particular, because when we write these questions, we really are trying to come up with problems that would neutralize calculators, Google apps, and things like that. And so these are a good example. They're always unique, right? So you won't have seen these problems before. You might have done similar problems in class during the year, but you haven't seen these problems before. So they're going to give you really good experience for what the exam might look like. And so this is BC2, and I'm going to kind of skip past part A, but you can see how this connects to what Tony did in the beginning with some product rule. And we're going to have product rule with a little bit of chain rule involved. So kind of a mixture of two rules there. But I want to briefly look at part B, just to get us a little bit more practice with the idea of chain rule, recognizing compositions. And so we want to find k prime of 2. Whenever the AP exam says find k prime of a number, or f prime of a number, it's always a really good idea to just find the derivative with x first, right? Don't worry about plugging that number in until you have an equation for k prime, right? Let's kind of break this down. So k prime, we're going to use the chain rule. We take the outside's derivative and we leave the inside the same, and then we multiply by the chain rule of the derivative of the inside, which in this case would just be f prime of x. So now we have a nice equation for k prime, and we can very quickly find k prime at 2 by just plugging in 2 for our x values. And so we have g prime of f of 2 times f prime of 2. And then we're going to go to our table and find some of these values. The first thing I need to find is f of 2. So looking at the table, there's my f, and here's 2, and we get 4 for that value. So we get g prime of 4 times f prime of 2. And I think the biggest mistake that Tony and I probably see students make on these problems is they just go too fast and they read the table too quickly and they grab the wrong number, not because they don't understand the math, but because they just went too fast, right? So make sure you're pulling the correct numbers. Or we see a lot of students that see this composition and they treat it like a product instead of a composition. Make sure you realize a composition is going to be a chain rule problem. And then we have g prime of 4, going back to our table, is just going to be 2. And then f prime of 2 is just going to be 3, and then 2 times 3 is 6. And so k prime of 2 in this case is nice and easy as 6. This was a pretty straightforward computation problem, but think about some other twists the College Board might give you on the exam on this exact same type of questions, because remember, the College Board wants to see if not just that you can compute things, not just that you can do some calculus procedures, they want to make sure you really understand what it is you're doing. Because sometimes we get so caught up in formulas and algorithms and procedures, we don't spend enough time to step back and think what we found, right? And so one application of k prime, they might have asked this question some different ways, right? What if they had asked, find the instantaneous rate of change of k at x equals 2, right? Instantaneous rate of change is kind of a verbal way of asking for k prime. Or what if they had said, find the slope of the tangent line to k at x equals 2. Remember, the derivative of a function is equivalent to the slope of the tangent line of that function, right? So a lot of ways they might ask that problem. We have to make sure we understand they're not just going to always tell you find k prime. They might use some words, and then you're going to have to connect that to finding what k prime is. So we're going to jump ahead, and I want to look at, for the last example today, one more integration problem. We did a derivative, and now we're going to do an integration problem with this table. I really like this problem because it's a BC integration problem. How do I know it's BC? When I see that infinity symbol on the top, I know that's a BC special topic, right? We don't have to deal with that in Calc AB with integration. That's an example of an improper integral. Remember, our fundamental theorem of calculus, the way it works is we have to have real numbers on our limits. Infinity is not a number, a real number, so we can't use the fundamental theorem. Now, my students always point out to me, but if I do it and just plug infinity in, I still get the same answer. That's because you're understanding what's happening, but your notation, technically, you're not using the theorem properly. And so you're not going to be having proper notation, which means you're not going to be eligible to earn all the points. And so remember, when we see an infinity symbol as a limit, we have to write this using limit notation. And we use that, b or some other variable. We say, well, let's take the limit as b approaches infinity of this integral. And we're going to approach this integral where b is a real number now, right? It's kind of it feels a little bit like smoke and mirrors sometimes when you say that you're doing it this way, but b is a number. And once we find the integral with the number, then we can apply a limit to see what happens as that number approaches infinity. So we are going to have to do some u substitution here. We have some parentheses that always becomes u sub. U is going to be 2x, and then du is going to be 2 dx. And then a little bit of a quick fix here is going to give me a 2 here and a 1/2 in front, kind of we did before. There's my favorite, 2 and 1/2. I'll have to keep that in mind for a future question writing that I don't keep using 2 and 1/2. And then if I apply this in terms of u, we're going to have the integral with 1/2 in front of g prime of u du. And just like before, we really do need to change our limits again, right? And so if u is 2x, my lower limit just becomes 2. And if upper limit's b, I plug that in, we're going to end up getting 2b up here. And then we're going to apply our integration techniques. We have the limit as b goes to infinity of 1/2. My infinity sign became an 8 magically. 1/2. And then what is the integral of g prime? Well, we could do the fundamental theorem. Integral of g prime is just g, and then we're going from 2 to 2b. And notice how I'm keeping this limit every step of the way. And what we're doing is I'm just going to plug in, we're going to evaluate the same way we would any other problem. We're going to plug in the upper limit, and we're going to plug in the lower limit. And then once we do that, then we're going to apply the limit, right? And so here, if I try to plug in infinity, I end up getting g of infinity, right? It's going to be a 1/2, and I'm going to have g of infinity. Well, how are we going to know g of infinity when that's nowhere on the table? And that's where this stem comes in. X is greater than 0, and it says g has a horizontal asymptote of y equal 5. And remember, when you have a horizontal asymptote, that means the limit as x goes to infinity or negative infinity of that function approaches that value. Well, we know that we can't take the limit as x goes to negative infinity because our domain is for positive numbers and 0 only. So the only way to have a horizontal asymptote is if the limit as x approaches infinity of g is 5. So we have to make that connection between horizontal asymptotes and limits at infinity in this case. And so here, I actually can evaluate this. And so we're going to get 1/2. And then the limit as b goes to infinity here is going to be g of infinity. Well, that's going to be our horizontal asymptote of 5 minus g of 2. And g of 2 is simply 9. So we're going to get 1/2 times 5 minus 9, which I believe is just going to end up giving us an answer of -2. So pay close attention to the limit notation. That's going to be a really big part of earning all those points on an improper integral. And then also pay attention to the idea of connecting horizontal asymptotes to limits at infinity. And then don't forget, when we say a function has a horizontal asymptote, in general, that doesn't mean that x has to approach infinity. X could also approach negative infinity, right? So horizontal asymptotes can occur in either direction, but in this special case, we restricted our graph to greater than or equal to 0. So there's no way to get to negative infinity. So we want to share those couple problems with you. A whole bunch of extra problems on here you can try, and I hope that you'll try them out. Don't forget the answers will be on there later tonight. And then this is another example on here. So as always, we have a couple of surprises. So before Tony reads the tweets out, after the tweets, a couple of surprises today, and then we will talk about what's coming up tomorrow, the rest of this week, and then moving on. So Tony, Tweets with Tony is back in session. What do we have today?
For our AP Teachers Rock, we want to give a special shout out to Ms. Hecht from Chaparral High School for being a great Calc BC teacher. Her method of always covering our homework assignments in depth have really helped me understand the topics on another level. So thank you, Ms. Hecht, and all the students from Chaparral High School. AP Students Rock, we've got a special shout out for an individual that I know. So proud of the BC Calc students from the 7, that would be Glendale Union School District, just outside of Phoenix, Arizona. So proud of them, who show class and dignity by showing up virtually and in person each day to be better at calculus. You'll be the one solving problems tomorrow. I am proud of you. And we want to extend a special thank you to an amazing rock star of a teacher, Kim Thomas, who sent that particular tweet to us. So thank you to everyone, and keep those tweets coming.
Yes, absolutely. Keep the tweets coming. We love them. Don't forget our AP Calc exam information. Tony and I have been gearing these lessons around this. We haven't been spending much time recently talking about it, but make sure you take note of the date and the time for your time zone, and then what's going on. And then we'll spend more time talking about that in the coming weeks as we get closer to the exam. And then tomorrow, Fundamental Theorem of Calculus. This is a pretty important lesson, Tony. Would you even almost call it fundamental?
I think it is a fundamental lesson, no doubt.
All right. I think we might have just lost our remaining viewers after that joke, but it'll be a really, really important topic that we'll see throughout the exam. And we've done a lot of that already in these last couple lessons. So just be an extension of that and more formalizing of that. Don't forget, we have some technology help if you need it. So always keep in mind that website, cb.org.tech or /tech, if you or anybody you know might have some device or internet access issues and need to get some help, please do that sooner rather than later. That way you can make sure that you have exactly what you need to take the test when it's time. And so thanks for watching. Surprise number one, here we go. We have our dog or cat of the day. So I get lots of dog photos and pictures and things sent to me. So I thought we'd share some of them. So this is our dog of the day. This is Maggie Grace. She's an Australian Shepherd. And because I am leading this, I get to have some bias in my selection process. So I actually chose for the first one of my own students, Emily's dog. It's a brand new puppy, so I had to give her airtime on there as well. We'll see how jealous Buddy and Wimpy become. But if you have a favorite dog or cat or any pet really, feel free to tweet to us, right? At PasswaterB or at AP Calc Teacher. Notice the spelling of both of those. If you tweet at us, maybe your dog or cat or pet or fish or whatever you have, lion, tiger, will make it on the air for our dog or cat of the day. So with that said, I think our final surprise today is we might get Grover back, I heard, to show us some of his dance moves. Is that right, Tony?
Hello, everybody.
Grover, are you ready to jam out as we exit here today?
Yes, I am, and thank you so much for being such a good teacher today, Bryan. I think I start to understand calculus.
Show me what you got, Grover.
Yes, AP Calc. Welcome you to AP Calc. Yes,